Thanks a lot. Don't worry, I'm just tired. I'm not, nothing exciting is gonna happen. Okay, so, all right. Did you? Okay, so we're gonna work over a perfect field. If you are worried because you are used to work over closed fields, just imagine closed fields. It's just not going to be that interesting. As we saw yesterday, Sarkisov program for surfaces over an algebraically closed field doesn't give us that much more information than the Noether-Castelnuovo theorem. So I'm just going to remind you. So this means any irreducible polynomial over K. So with what is has only simple roots over K bar. Okay, so imagine any field of characteristic 0, or if you want, finite fields, but not function fields over finite fields. Those not. And most of the examples I'm going to give you are going to be over R, because for me R is the nicest non-closed field. It's the field that is closest to being closed, some sort, but it isn't. Okay, so let me repeat a bit things on varieties, on K varieties or on K forms. That's more my point of view. So, okay. So a K variety would be a variety, a scheme over spec of K, and a K form is really a variety over K bar, and we put a Galois group on it. So we have a variety Y over K bar plus an action of the total Galois group of K bar over K. And this makes sense because we chose our field to be perfect. Okay, so basically, this tells us we can use all the geometric information of Y plus group action. So anything's going to be equivariant or invariant under the Galois group. And so we can use our intuition that we have on Y. So X. This is where X. So for me, this is a K form of Y, and let's say this is my X, this is my surface X, or my variety X, and then we have we can think X. I can look at it over. So what I'm saying is not entirely correct. There is a bijection between varieties over K and K forms. But what I think of it is that I have a variety over k, I look at it as the same variety over k bar. So if you think of your variety as given by coefficients by polynomials with coefficients of k in a projective space, you look at the same variety but then over k bar, and that's x at k bar, and here the Galois group is acting naturally on spec k bar. Oh, sorry. What did I? Yes. Okay. All right. So, what the examples I started with yesterday were P1 over R. So this is P1 over C plus the action of the Galois group of C over R. This is just a group of order 2, and the generator does complex conjugation on each on U and V. Starting to not enjoy the forgetfulness. And then we have the so-called empty conic. So this is P1 over C plus, again, the action of an action of a Galois group of the Galois group of C over R that does UV maps to minus V bar U bar. And the way you can distinguish them geometrically, like that's a part of why I like R, because there's the fixed point set of the Galois group is called the set of real points of a variety, and it gives you plenty of information. So here, so P1R, the real points. So this is the set of Galois fixed points. This is S isomorphic to S1, and for the empty conic, say this is E. So the set of real points, again, this is the set of Galois fixed points. This is empty. Okay, and for smooth real varieties having for curves certainly, and for surfaces having no real points or having real points is something that is invariant under birational maps. Because the set of real points is Zariski dense, you cannot just make it disappear by applying a birational map. They are not just on a curve that you can contract. Okay. And so these are examples. So you can have many real forms on the same complex variety. And then, so they're okay. For projective spaces, they're easy. They're not so many. For Pn and odd, there are just 2 real forms, and then for the even dimension, there's just 1. So, okay, so for P2, I'm just writing down 1, and that's just because there's only 1. So x, y, z. Bar, y bar, z bar. Okay. And then in P2, we have, so we've seen maybe a bunch of times, there's a pencil of lines in P2. I can take a point, 1, 0, 0, the pencil of lines through it. So that's a y plus b z equal to 0, the family. I should maybe be more precise. And then there's a second pencil that over C we don't really care about because it's just basically one can be transformed to the other by a birational map, but over R we cannot transform one to the other by a birational map. And that's if I choose two pairs of conjugate points, so one I0, one minus I0, and then 0, 1, I, and then 0, 1, minus I. So because of my, I look at my P2 with a Galois action, one point is an orbit under the action. Okay, so these 2 points, these count as 1 point. I always, whatever I do to them, I have to do it to both of them. I blow up one, I have to blow up the other, so that what I blow up is equivariant under the action, or invariant. So if I want to have a pencil of conics through one I0, all these conics also have to pass through the sibling of the point, 1 minus I0. And then, so here I have A square plus Y square, Z square plus B xz equal to 0. So this is also a pencil. And over C, I can map, I can choose, so over C, I take a quadratic birational map with base points, for instance, 1 I0, 1 minus I0, and then 0, 1 minus I. Okay, and I apply, I will redo the picture here. Okay. I'll apply this map, and I'll send, so the conics passing through these 3 points, they're going to be sent to lines, not passing through the base points of the inverse. They're just going to be general lines. So what I send it to is a pencil of lines. Okay. So this is my, green and red are not good. I'll take yellow. Now, this type of map is not defined over R because I chose a birational map that has one pair of conjugate base points, but then a third non-real point, and we forgot to include its sibling, so this is not defined over R. But only over C. So this is why we don't really care about this pencil over C, but we care about it over R. We cannot transform this pencil into this pencil over R. So while over C, there is up to conjugation one group that preserves the pencil of lines through a point, over R there are 2 types of such groups. One that preserves the pencil of lines through a point, and one that preserves a pencil of conics through 4 points, to 2 pairs of conjugate points. So, okay, so let me also write down the things that I used in my explanation, but I possibly should have written them down before. So a point in our x, so x, maybe x was our k variety. So this is just a Galois orbit of a point in xk. So for instance, 1 I0 and 1 minus I0 in P2. Okay, let me write it like this. In a sort of more, we can also write this as a zero set of z equal to 0 and then x squared plus y squared equal to 0. So if you live in the world where you don't have a Galois orbit, this is your point, right? Okay. Xk bar, thank you. Yes, yeah, absolutely. Yeah. Okay. And then again, the same for curves. So a curve in X is a Galois orbit of a curve in xk bar, and so on. So if we're in a higher dimensional variety, a surface in X is a Galois orbit of a surface in xk bar, etc. And here, a simple example would be like the two lines, x plus iy equal to 0, and x minus iy equal to 0. Okay, they intersect at 0, 0, 1. This point is invariant under the Galois action, but the Galois action exchanges these two lines. And, well, this is the conic x squared plus y squared equal to 0 in P2R. Okay, then something very important for anything you want to do over, like with this point of view, is that the Galois action preserves intersection of divisors or intersections of curves of divisors. Sorry, and curves. So if I have a divisor, and see a curve, then I have d times c is d g, so an element in the Galois group, times c g. So this is the image of d under this element g, and this is the image of c under the element g. Divisor curve in xk bar. Okay, and then right, and then what I used here to say that this is not defined over R is actually my definition of what does it mean to be R birational or C birational or K birational. So if X is a rational map from X to Y, this is the case if and only if. So we have a commutative diagram for all elements of the Galois group. B is in the Galois group. So we apply F tensor the identity. If you remember that xk bar and yk bar were just tensorizing with back of k bar. And then on both sides, we can apply g, and we get back xk bar and yk bar. And here, this has to commute with f tensor, the identity. So for example, for x and y equal to p2, so f is rational if and only if the coefficients of f are defined, are actually in R. In K, sorry, I will, yeah, okay. You can replace R by K. Okay, and then, so if f is birational, then all base points are pairs of, or either real points, so fixed by the Galois action, or they are pair of conjugate points. Okay, so all base points are Galois orbits. We say here k, here k as well, and then plus all contracted curves are Galois orbits. So this is what I used secretly to say that this is not defined over R. Okay, and then a very, very nice property that is very specific to our choice of fields is that X is smooth if and only if X of k bar is smooth. So because this is not true in general over imperfect fields. I mean, it's, sorry. Ah, you're right, yes. So let me say, you're right, I agree. Okay, let me just put this out and say also smooth is regular, and this is not true in general or imperfect fields. Better? Sorry, here. Da-da-da. Sorry, that is. But because if you compose with. I mean, fair enough. Okay. Good. So this for me. What did I? No, this is not what you wanted. Okay. Any other? Yes. Here. Um, Can you repeat what you just said? Sorry. Yes. It is not smooth over R. Not a smooth conic over R. There's a singularity. So this in P2 is singular. Yeah. Any other questions or comments? I mean, I'm happy if you have questions or comments. Also, please let me know if I forget to write down something. It's pregnancy, loss of memory is a real thing, and I'm forgetting Zoom calls all the time. So I think in my last few course lectures of my regular lectures, I sometimes accidentally jumped over a theorem because I just forgot that I haven't wrote it down yet. Students had to remind me. All right, okay. So now we have our K varieties, well, our K forms, the way I see them anyway. And now let's get down to the more gritty business of defining what is a Sarkisov link. So first, what is a del Pezzo surface? Have you seen what it is last week? Okay, all right, okay. So first thing that I learned recently, it's a big D. Okay, it's not a small d. It's a rule for Italian names that have a del in front of it. Okay. If you write down the first name plus the last name, the del becomes small. But if you just write the last name, it's big D. All right. So this is a smooth projective surface such that minus kx, so the canonical divisor, of x times any curve is positive. Okay, and this condition, people also say that minus kx is ample. Okay, and so if the base field is algebraically closed, then the Pezzo surfaces, they are very nicely classified. So then either it is P1 cross P1 or P2 blown up in at most 8 points. In general position. And in general position, bless you, means no 3 on a line, no 6 on a conic, and no 8 of them on a cubic where one point is the singular point of the cubic. So basically, these are just ways to say that when I blow up, I should not get curves of self-intersection -2. Because in fact, what this also means is that do we have X morphic or X? You have no curves on X, self-intersection -2. So X sorry, yeah, we are over K bar, very good. So X has X has no curves of self-intersection at most 2, and it has only a finite number of curves of self-intersection -1. Okay. Rational curves. No. Rational curves. No. Yeah. Okay. Right now, if we pass to fields that are not closed, oh, right, so also a second remark. So if C is a curve in X, that means C over K bar is a Galois orbit. Okay. And then Kx times C, this is just Kx bar times C1 plus C2, etc. up to Cn. Okay, so because the Galois, right, and these all have the same self-intersection. So because, yes, yeah, you're okay. Because the Galois group doesn't change intersections, sort of, that's my agreement here. So because of this, we have, so if X is del Pezzo, then also this is actually equivalent to xk bar being del Pezzo. Because, right, so here, maybe I can write this. So this is x k bar times n. Okay, so if the intersection of the anticanonical, sorry, oh my God, the anticanonical divisor is positive against all curves, the same is true over k bar and vice versa. I told you to tell me if I forget dumb stuff. I am disappointed by you. I feel okay. Okay. All right. Okay, and now you can imagine that, okay, if we have a del Pezzo surface over K bar, and we put some funny form on it, we'll still have a del Pezzo surface, but it's not one of these anymore. Okay, so for instance, so we look at x, be a quadric, y equal to w squared plus z squared in P3 over R. Now over C, this is just isomorphic to xy equal to wz, right? Because I can write w squared plus z squared. This is maybe a bit small. Okay, I can write w squared plus z squared equal to x plus w plus I z, w minus I z. Okay, so I get here. And this is isomorphic to P1 cross P1. If you haven't seen this, this is an exercise. I mean, you can find the isomorphism explicitly. All right. Okay, so X is del Pezzo. But because here, so in this variety over C, the Galois group of C over R exchanges these two parts. This actually means, if you write down the isomorphism, that the Galois group exchanges these two fibrations. Okay. So, okay, so in particular, if I look at this lovely P1 cross P1, what the Galois group does is something like this. Okay. And in particular, so this variety has picker rank 2, so the space of curves is generated by two curves, one in each vibration, but now I'm exchanging them. So the new picker rank is 1. Okay. So this type of classification doesn't hold over non-closed fields in general. Okay, so this is the first definition that we need for our Sarkisov links in general, the Pezzo surfaces. And the second one is conic fibrations. So here, you have to be a bit careful because in literature you find different notions of what this means or what people mean by a conic bundle, etc., etc. It's not always the same. So this is so X has maybe I'll write. So this is a morphism. That is surjective, okay, between a surface, smooth, projective surface, and B is a point B is a smooth curve. All right, such that the anti-canonical divisor intersects positively any curve that is contracted by this morphism. Okay. And also, yeah, all fibers have the same dimension. This is okay. Now, for an example, so maybe a remark. So what happens if K is algebraically closed? Then this condition tells you that every contracted curve is a P1. Okay. Is a P1 or two P1s that intersect this way. So in particular, what we have here is something that in general is a conic bundle, or what you can imagine, a conic bundle, and some fibers are degenerate conics. So, I actually don't, so good point. I'm sorry? It can happen over surfaces. I mean, I can. Yeah, no, it cannot. Yeah, you're right. Yeah, yeah, you're right. Yeah, okay, yeah. Yeah, okay, yeah, okay, so it's just this. Thank you. Okay, so X to B, some curve, and then we have P1s and some singular fibers. And examples are the Hirzebruch surfaces that we've seen already. And then, so if I have a Hirzebruch surface, I can take a point. I can take points in distinct fibers and blow them up. And that's still a conic fibration. Okay. I can also, so if K is R, if K is R, this remark translates to the fact that every curve in the fiber, every fiber is a form of P1. So it's P1 or the empty conic, okay, that we have over there. And then these type of fibers where either it's possible that both fibers are P1s over R, or that they're P1s over C and they're conjugate. Okay, so they are degenerate, really degenerate conics. So for instance, if I have my my funny quadric surface, in P3, okay, this is, I'm writing it down as P1 cross P1 together with the Galois action that exchanges the vibrations. I can take two real points. So let's say this is let's say this is 1, 0, 1, 0, and the other one 0, 1, 0, 1. So these are both invariant under the Galois action. They are real points. And then I take the 1, 1 curves passing through these points. So and then when I blow up the red points, what I will get is a Pezzo surface of degree 6. Okay, we have the two exceptional divisors that are -1 curves. And now I'm freeing up the pencil of these curves. And this is a conic bundle. I can project onto maybe I'll write it down in a more natural form for me. So this is okay. Now you can see that this is a conic bundle, and it has two singular fibers, okay. And locally we can write this as as x squared plus y squared minus t z squared equal to 0 in P2 over R times A1 over R. So here is the t, this is x, y, z. Let me check whether I have the right sign here, because since we're over R, signs are important. So for t, okay, let me think for a second to myself. I will talk to myself. You're free to listen. Okay, for t negative, I have no real points, and for t positive, I have real points. Okay, so yeah, this is the right one. And in fact, this is sort of such a description you can always get for conic bundles. You can always find that there's an open set of your curve B over which you can embed the bundle into a P2 times AR or something, but maybe not A, but a curve. And then the conic vibration is given by a quadratic vibration, by a quadratic equation with coefficients over your open set. So conic vibrations are locally something given by quadratic equations, is what I want to say. All right. Now, okay. Now let me sort of sum up these two definitions in one type of, in one word, and that is a Fourier vibration, or a rank 1 vibration, if you will. So this is a morphism, a surjective morphism from X to B from a surface X that is smooth on projective and B is a point or a curve, okay, and such that or a smooth curve. Right. So the anti-canonical divisor is positive, intersects positively any of the fibers, so exactly like here. So and then the relative picarang, this is the dimension of the vector space of curves in X contracted by pi. This is 1. And, well, I should maybe add this. So P has, all fibers are connected. Okay. I should add this here. And then X itself is a Mori fiber space. So this definition sort of unites the definition of the Pezzo surfaces of picker rank 1 and conic fibrations of picker rank 1. Because, so if B is a curve, what you have, this definition is exactly this one, except that I ask for the relative picker rank to be 1. So all the curves that I contract, they should be equivalent, linearly, or Q equivalent, linearly equivalent. And if I have if B is a point, then what is written here is that, so then any curve is contracted, if B is a point, and then the anti-canonical divisor intersects every curve positively. So what is written here, in that case, is exactly the definition of a del Pezzo surface, plus I ask for the picker rank to be 1. So this in itself is not it's del Pezzo, but it does not have picker rank 1. Okay? One has picker rank 1. Well, if I blow up 1 point, which I'm allowed, I get a del Pezzo surface, but it is not of rank 1. So it is not, so it does not satisfy the definition here when B is a point, but P1 cross P1 satisfies very much this definition when B is a curve. And also when I blow up a point in P2, I get the of 1, a Hirzebruch surface. It is del Pezzo. It has picker rank 2, and it satisfies this definition with B equal to P1. All right. Do you have any questions on the definition X? Perfect. I'm sorry? Yes. Yeah. Thank you. Are there any other questions on these definitions? So the Pezzo surface, conic fibration, and a Mori fibration or a Mori fiber space. Mm-hmm. Yes. I'm sorry? Yes. Yeah. Yeah. Maybe I will add this. Yeah. Curves over K. Any other questions? Okay, let me write down the examples that I just mentioned. So P2 with a morphism to a point is a Mori vibration. So F1 to a point E. So this is il Pezzo. That is not a Mori vibration. Since the Picard number, the relative Picard number over a point, this is just the Picard number itself. This is 2, okay, but F1 with its projection to P1, this is a Mori vibration. Okay, and then, so if we take back the example of the funny conic vibration that has 2 over R, that has 2 singular fibers. So I'm gonna write it down again. This is xy equal to z squared plus y squared. I'm realizing that I'm making, no, this is okay. I blow up. Then I have a vibration over P1, R. So this is the Mori vibration. Okay. For conic bundles, you can think of a Mori vibration as the property of being minimal. If I contract anything, I lose the property of being a conic vibration. So I cannot contract any of the vertical curves. But this is not a Mori vibration over C. Because over C, okay, all these fibers of P1 cross P1, they have self-intersection 0. And then when I blow up these 2 points, they get self-intersection -1. Maybe I'll put the exceptional divisors in red. Okay, and over C, I can contract this curve and this curve if I like, or just this curve and this curve. And I will get to a Hirzebruch surface. And the Hirzebruch surface is a Mori vibration. It has relative Picard rank 1. So I can I can contract, for instance, these two curves, and then I'll get to, so here the lower red line keeps itself intersection -1. The upper one, since I contract two curves intersecting it, it gets to itself intersection 1. And then I have only non-singular fibers. And this is F1. Okay. And I can do this over P1C. This is X. And so this one has a relative picker rank 2, right? Relative picker rank 1. And this one has, so here we have relative picker rank 1, and so here we have relative picker rank 3, because I blew down two things. So this is not a Morey fibration, but here the two curves, the two singular fibers, I cannot contract anything over R because they are conjugate. So the Galois action, the Galois action I have to, okay, the Galois action exchanges the fibrations, and then I get to exchanging the parts of the fibration. Sorry. I just realized a mistake, which is maybe good. So if the Galois action exchanges these two fibrations, it needs to exchange these 2 points. So I cannot, it was a mistake of mine to choose these points to be real. They should be complex conjugates. So here they should be something like this. And I'll fix it in this example. Here, I cannot contract any component, geometric component of the singular fibers. So the relative picker rank is 1. Sorry for the mess up with the point. Are these examples okay for everyone? So what I want to say is that, okay, we have this, so a Morey fibration, if you look at, if it is a conic bundle, being a Morey fibration is the same as having relative picker rank 1. And this is exactly saying I cannot contract anything in the fibers anymore without losing the conic bundle structure. So here, the singular fibers, their geometric components, they are conjugate. So if I contract one, I also have to contract the other one. But if I contract this one, the other one becomes a curve of self-intersection 0, and I'm not allowed to contract any of those. I'm only allowed to contract -1 curves. So here, I cannot contract anything without losing the conic bundle structure. So this is a Morey fibration. It's minimal. Now if I pass to C, these become lonely -1 curves, and I can contract any one of those, or any two of those if they are disjoint. And if I contract these, I get an F1, which is already minimal, but this is then not minimal. Okay. And so just maybe the way I was thinking about the points. So if I want these two fibers to be a complex conjugate, the complex conjugation sends this one onto sends this one. So it has to send this red curve onto this red curve, right? They have to be conjugate as well. So these have to be conjugate as well. I cannot choose them to be real fixed by the involution. Okay, this was the mistake I made. Okay. All right. And now, maybe a more accurate theorem. Oh no, this is 6, 14, 5. Okay, so I need to maybe make more precise the story of these papers. So I think that in Corti's paper, the history is written, so he heard the idea of one could make such a program from Miles Reed. And I think that Miles Reed, him, had this idea after hearing a talk by Sarkisov. Okay, so the idea of these two papers comes from so these two papers are based on an idea of Miles Reed. Corti says that there is some unofficial article that nobody can find, sadly, so we don't really know how Reed saw exactly the Sarkisov program. And yeah, so okay. Correction of history. So any birational map between fiber spaces. So I go from XB, and I have a birational map to X prime or B prime. The composition of Sarkisov links. And isomorphisms between Mori fiber spaces. So this theorem, it is a generalization of the theorems that you've seen yesterday, because yesterday I wrote down the theorem for P2 instead of Mori fiber spaces, but P2 is a Mori fiber space. And also, if you look at, maybe a comment, if you look at these two papers, both of them say that they are working over any field, but they're working over perfect fields, okay? So, Now let me repeat the list of Sarkisov links, or the definition of Sarkisov links. So basically, we have 4 types of Sarkisov links. We have type 1, we have type 2, we have type 3, and we have type 4. So type 4 is the easiest one to write down. So I have 2 Sarkisov links are particular birational maps between Mori fiber spaces. And there are 4 types. So I can have on a given Mori fiber space, I could have 2 different vibrations, conic vibrations, okay? Conic structures. This is a Mori fiber space, a curve, and B is also a curve. And so the general example that you saw was the exchange of the 2 vibrations of P1 cross P1. And like for OR, for instance, I could have P1 plus the empty conic. Let's say this is C, okay? And then I exchange the 2 fibers. In one fiber I go to P1, and in the other fiber I go to C. Also an option. For R. Okay. Then the links of type, link of type 1. So I have, what I do is I have a Mori fiber space over a point. Okay. This is a del Pezzo surface. Okay. And then I blow up. I have a birational map whose inverse is a birational morphism to another Mori fiber space. And a diagram that commutes this way. Okay. Now, here we have relative picker rank 1 by definition. And here we have relative picker rank 1. This is a curve. The relative picker rank of a curve onto a point is the space of all curves contracted onto the point. So this is 1. So the relative picker rank, so this means we have 1, 1, 1 for relative picker ranks, and they have to add up. So here we have relative picker rank 1. This means that this is the blow up of a point. I'm just saying that. So of 1 point. You can include it in the definition, or you can leave it out, and it follows from the properties. Okay, and then type 3 is exactly the opposite. So here, in type 1, the Sarkisov link is going up. Okay, and in type 3, it is going down. The link. And just in case, here is the link. Okay. And now type 2 is that I have two Mori fiber spaces that have a vibration to the same base. And then in each of them, I blow up one point, and I need to get a commutative diagram like this. So here you have two options. This is a curve. I'm sorry, I need to specify. And here B can be a point or a curve. Now, if B is a curve, this is an elementary transformation of conic vibration, of conic bundles, of conic fibrations, sort of like the one Jeremy used in his lecture last week. Maybe I will start with an example here. So this is the one that we see most often. We have P2 over a point. This is the Pezzo surface, so it's a Mori fibration over a point. And then I blow up maybe 1, 0, 0. And I'll get to F1, and F1 has a conic bundle structure above P1, and then I get here diagram. And here again the same. I have P1 over F1 over P1. I contract the -1 curve. I go to P2. That's a Mori fiber space over a point. Get my equation here. Okay, so here I'll make two examples as well. One for when B is a curve, and one for when B is a point. So if B is a curve, then I can go from the Hirzebruch surface, that's a Mori fiber space over P1, and I can blow up a point, maybe a rational point or an orbit of points. Okay. And then I can, so the exceptional divisor becomes this red -1 curve. The fiber is a fiber, they have self-intersection 0, becomes a -1 curve as well, and then I can contract the white -1 curve. And this makes the self-intersection of the special section increase. And we get to Fn -1. Please tell me if I made an error. Okay. So now if B is a point, we start with P2 over that point. Okay, that's our P2 is our x over B. Okay, and then I'll take the line z equal to 0, and on it, I'll do it over R. All right? Okay. On it, I'll take two conjugate points, one I0 and one minus I0, and I blow these up. So the line has self-intersection 1. If I blow up 2 points on it, it gets self-intersection -1, and then the two exceptional divisors have self-intersection -1. And now I can contract the -1 curve here, the white -1 curve. and I'll get to another surface. And the red lines, I contract a curve that intersects each of them once. So the new self-intersection will be 0. Okay, so where are we here? What surface do we end up with? A hint. So I have, geometrically, I have 2 pencils of conics passing through each point. These pencils, they're not really pencil of conics because the complex conjugation that I have on P2R exchanges them, right? So these are, so our Galois action exchanges these 2 red points and therefore also these 2 pencils. Now, if I blow up these 2 points simultaneously, the Galois action lifts to a Galois action here, and it exchanges these 2 red curves. The line z equal to 0 is invariant under the Galois action, so it is preserved by the Galois action. And when I blow up the red points, I free up the pencils. Again, they're not really pencils, they're exchanged by the Galois action. And then I contract the white curve, and I get that the pencils are like this. So you want to be a bit pedantic here. Each of these geometric lines has self-intersection 1. When I blow up the curve, they get self-intersection 0. When I blow up the points, the red points, then when I contract the -1 curve, that changes nothing at the self-intersection 0. So where I end up is geometrically on a P1 cross P1. So this is a real form of P1C cross P1C. But which one is it? So again, complex conjugation here exchanges the 2 red lines. So here it exchanges the 2 red lines. It exchanges the 2 pencils. So it exchanges the 2 fibrations of P1 cross P1. So so here, our Galois complex conjugation, the Galois group exchanges these. So we have is that this is y equal to w squared. Okay. And now we've already figured out vaguely that the pica rank of this form is 1. So P1 cross P1 over C, together with this Galois action that exchanges the 2 fibrations, this is a Mori fiber space. Okay, so we have, so if we look at the morphism that contracts everything, then this is also a Mori fiber space. Okay. So this is a link of type 2 between 2 Mori fiber spaces. Okay, I'll write it down maybe nicely. So we have P2 over a point, and then so this is our diagram. Do you have questions for this about this example? Of? Type 4, yes. So type 4 is that you have two Mori fiber spaces over a curve. And so no, you have a Mori fiber space that has two fibrations. And you consider first you get a sequence of Sarkisov links going to one Mori fibration, and then before you start another link of type 2, 3, you consider it with the other fibration. So what it doesn't mean that I can send this vibration onto this one. Okay. Maybe, I mean, maybe you can put this if you want. Now I see your face. So, yes. Yes. Yeah. So I can, I'm sorry, what did you say? Yes. Yes, we can, yeah, that's also, we can do that if you want, yeah. So the thing is, okay, Sarkisov links are defined up to isomorphisms of the Mori fiber space. Okay, because if I have a Mori fiber space, a Mori fibration, and I apply maybe an automorphism or an isomorphism, that gives me another Mori fiber space. And if I have, if I say, like if I wanted to be super pedantic, I could say F1 is the only conic bundle over C, over like smooth projective, blah, 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 with a special -1 section up to isomorphism. I could do that. Yeah, because it makes a difference, because I could just add here something else. So the isomorphism or an identity doesn't make any difference, whether I put an isomorphism here or the identity. I can put the identity. Yes, yeah. Yeah, then you add the isomorphisms between Mori fiber spaces. Yeah. So if you want, so here, for instance, the usual way to write it is to consider this the isomorphism that exchanges the fibers. But you can just as well say, okay, I just have P1 cross P1, and I have my two fibrations. And then I add the isomorphism exchanging the fibers. And I get here something like this. Sorry, then I need to. So both, I mean, you can use this as the example with the identity, or you can sort of follow Iskovsky and Gorty and say this is our link. It doesn't really make any difference also for the theorem. I know you're not happy. Sorry. A clear definition. Then let's go with equality here. So yes. Let's go with this one. fair. Yeah, okay, that's fair. Yeah. Yeah. Okay. Okay, fair enough. Yeah. Okay, that's fair. Okay. So, yeah. Yeah. But yeah. Okay. So there is a second, if we are on the discussion, there is a second type of discussion we should be having, and that's here. Should it be the identity over B or an isomorphism over B? I wrote the identity. But you know, we were having like when we generalized this theorem over imperfect fields, that were discussions we were having because, as you say, like for certain things it doesn't really matter much, but then you want to have a really rigid definition, you need to be clear on what it means. So, and yeah, yes, yeah. So this is an isomorphism between. Right. So I really want isomorphisms between the spaces, not necessarily the fibrations. Yeah. So okay. So y prime prime. So I don't need it to compute with the fibration. So yes? Do I? Are you sure? Yeah, okay, let's do it. Fair enough. Yeah, okay. Okay, let's put yeah, okay. Preserving between Mori and let's change it. Okay, very good. Mori vibrations. Sasha, any? Are you good? Okay. Do any of the slightly younger people have any questions? Comments? Yeah. Yes. Thank you. Yes. No, it is not obvious. Thank you. It's a okay. Um, yes. Yeah. Why do I have to add it? Not really. Why do I have to add this to the definition? I'm not really sure why. Okay. This piece of, okay. 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 Okay, fair enough. Very good. Okay, then I will. Okay. Okay. Okay, let me say here and so then let me delete this and just say minus kx is relatively. Maybe then we are more precise. Is everyone happy now? All right, then that's it for today, for me.